Stream. Okay. Alright, so I'm just checking the messages. Um, okay, so I got some questions about whether to zip up the folder. You can zip up the folder. All I really need is the source file, so it depends on whether people use Codeblocks or whether they use online GDB. Because if you use online GDB, there's only one single source file. If you're using the other approach, using Codeblocks, then there are multiple files.
Hey,
Although,
Professor, I think you're muted on,
oh,
actually, you're muted on Google
right,
Meet.
yeah, you're
Yeah.
right. There we go. Sorry. Alrighty. Alright, so we got more people coming in. Alright, so I was just talking about how to turn in the homework assignment. Whether to zip it or not. If you're using online GDB, there's no need to zip because there's only one source file. Because everything has to combine into one single source file to work in online GDB. If you're using Codeblocks, then you do have multiple files. Even though you're not supposed to change any one of the other files, just for the sake of being able to that I can open up the project easily, you can zip up the entire folder and turn that in. So there's that. And let me go back to the class channel.
If you have time, do you think you could go over how to set up GDB in Codeblocks? I wasn't able to figure that out.
Okay, sure. All right. So, well, this is a good time to actually talk about the second floating point assignment, which is the oops, that is not it. The positive exponent homework assignment. There we go. So this one is due in a week. So once again, you have about a week to work on this one. Let's see. Let's go to preview. I'm not sure whether it has. Yep, it still has the same archive file, so I can do the same thing here. So this instruction is only applicable for people who want to use Codeblocks, which is not required. And I want to download. There we go. And I'm gonna save the file to my temp folder. There we go. All right. So the instruction I'm giving you guys, this part of this is kind of Linux specific, which means I'm using the command line to do some of the work. But you certainly can use whatever tool Windows has to unzip the folder. There we go. And I'm just gonna use a new tab. Unzip double one. Okay. Which unzip into its own folder. And once we get into the folder, we can find all the files. And to be more specific, we have the CBP file. Now, if you do this in Windows, depending on how you installed Codeblocks, it may or may not work right out of the box. So that could be one of the issues that some of you have encountered. So there we go. We have Codeblocks. Alright, so moving the Codeblocks window into view. There we go. Alright. So from inside Codeblocks, I can go to the folder and open the CBP file, Codeblocks project file. There we go. So it is this one over here. Double click on it. Alright, so once you're in Codeblocks, once you open the project, you have to go to project and then go to set programs arguments. And once you get there, you will see two different targets, and we're going to use the debug target. And then you just set up the program argument, which is -n, followed by the base 10 scientific notation, which you can use whatever you want. Okay, so I'm just going to use 1.23 times 10 to the power of -50, and then you click OK. And all I'm going to do here, obviously this is not going to work, right? This is just an infinite loop, so I'm just going to put a breakpoint here and debug the code. So I use debug start, and the program compiles. Oh, it complains about cannot set controlling terminal. Huh. That is new. I have not seen this before. Alright, so let's see. No, it still works. Okay, so it still works, because I can still see all the helps here. So once we get here, we can use all the GDB commands such as print, and you can see how the mantissa is 123, the exponent of 10 is -52, and so on. So that's how you can use Codeblocks to debug the program. If you're using Windows, you have to be careful because there are several packages that you can download. Let me see if there are any questions about using Codeblocks. Okay, so I don't see any questions regarding Codeblocks. Very good. So if you go to the Codeblocks download link, there are several of these files. Okay, so if you go to binary releases, there are several, and they are not all the same. So what you need to do is to get the correct one. You do want to include MINGW, and let's see. The one that is a zip file is good from the sense that perspective that it would just unzip into a folder. You can put it into a portable device like a thumb drive, and it would work. The difference between this one and this one over here is the one that doesn't say 32-bit, it's 64-bit, and then the one that does say 32-bit is for older operating systems, older Windows, where you want to run it in 32-bit mode. So that's all I can show because I'm running Linux right now, and it would take much too long to start up my Windows virtual machine. So this is all I can show you at this point. Alright, cool. And let me check. Alright, so there are no additional questions. So does that address the question earlier?
I'm going to have to go back and check it later, but probably.
Okay. Alright. So I'm going to close this tab. And the new assignment is for positive exponent. So this one basically just starts off with a exp10 that is positive, probably a big one too. So basically we want to get exp10 down to 0, but at the same time exp2 will have to go up. So in this particular example, I gave I have a trace of a particular example. So in this case, I'm using 1.2345678 times 10 to the power of 30, and this gives you an idea of how the mantissa is changing, and how the exp10 is changing, and how exp2 is changing along the way too. So there's that. Do we have any additional questions about the homework assignment? This one is due in a week. Okay, I don't see any questions.
Yeah, I have a quick question.
Yeah, go ahead.
So could we just modify the code we turned in for the last assignment?
Yes, absolutely.
Okay.
Okay, I need to know what it is referring to. Alright, so I got a few people typing in the text channel, so I'm gonna wait a little bit until... Okay. Yeah, well, sometimes, It is due 1 week from today. Yes, so if you look at the due date... Okay, let me see where it is. The due date... It shows right here. So due date is March 9th at 5:30 p.m. It's similar logic, Victor. I wouldn't say it's exactly the same logic.
Tack, what window or subsection did you go to in Codeblocks to set the target?
Oh, okay. I can show you that. Let me see if Codeblocks is still open. Yep, it is still open. So to set up GDB, you go to, I think it's under Tools. Maybe. I cannot remember where. Okay, so maybe under Settings. Yep, so it's under Settings. So go to Settings, go to Debugger, and then go to GDB, CDB, Debugger, and look at the drop-down box. Go to Default, and the executable path is where you need to set where you find GDB, which is probably going to be in a subfolder of Codeblocks itself. I do not know why it does not come pre-configured correctly in Windows, but that seems to be the case at least in previous years. Alright, so I'm looking at the text channel. So we got one new text that says, is that also today's lab like last homework? Similar, as I said, similar, but not exactly the same. So this time, your program only has to deal with a positive exponent of 10, but you need to make sure that your program can handle a really large exponent of 10, something like 50, okay? Just so that the mantissa by itself is not sufficient to handle the situation.
And we're not normalizing the mantissa.
And we are not normalizing. That is correct. So the requirement that the mantissa needs to use all 64 bits still applies to the assignment that you're going to work on this week.
Well, don't we have to make the 63rd bit 1? So wouldn't that be, in a sense, normalizing it?
I suppose, but it's not normalizing to the double precision floating point number standard, because that one only needs 52 bits for the fractional part of the mantissa. So the one that I'm specifying in the homework assignment uses all 64 bits of the mantissa.
Right. Okay.
Yeah. So the idea of using all 64 bits is so that we can preserve as much precision as possible during the conversion. One thing I found was this way of doing it, is actually just very, very slightly more precise compared to scanf and other parsing ability or parsing base conversion logic that is built into C and C++. So it is good to preserve all 64 bits until the very last moment when we say, okay, now we need to only get 53 out of the 64 bits. Then we can shift things out at that point. Alright, so there are quite a few traffic going on. Okay, so I'm just going to start with the one at 542. You do not have to use Codeblocks. No. Just like in the previous one. So if you have been using online GDB already, you can use the program that you just turned in today to continue, and you specify the additional logic to handle the positive exponent. Next one, we have not done this because the previous, unless somebody already did the positive exponent in the previous assignment. Next one, are we going to start having week-long labs? No, it's just this is one of the few labs where it will take more time. The time complexity, that's an interesting one. It is not n squared. It is not going to be n squared, because we know it's going to be. It has to do with the largest representation, so we know that there won't be any more shifting than 2047 because altogether that's the extent of exp2, so we know we cannot exceed that. So it's not going to be n squared. And then the next one, yes. So if you did it today, if you also have the logic of handling the positive exponent, you can turn it in today. But it doesn't hurt to double check and make sure that it works before you turn it in, because you do have a whole week before you have to turn that in. Next one up. Yeah, the code I turned in works for positive exponents too. As I said, it doesn't hurt to double check that. Yes. Easy week, more or less. But we are introducing new material in the class too, so that part, is going to be a little bit, you know, it'll be interesting. Is it possible for us to look at your quiz attempts? I do think so. And then the last message is, if we're using online GDB, do we just turn in the file? Yes. So you turn in main.c, which is just one single source file. It is the monolithic approach to do things, which is not ideal, but I find that online GDB is a very usable interface for writing programs like this. Okay, it's not good for large projects, but for smaller projects like this, it's fine. Alrighty. So I think we are good here. And I'm just gonna hover my pointer over Discord, just so that I can clear all the messages. There we go. Alright. So with that specified, what is muted? It says it's muted. The quiz. Muted. Oh, maybe I haven't.
Quiz opens after the class, doesn't it?
Yeah. So let me close this first. Okay. So maybe I have not released it. Okay. Let me go back. Double check. I thought I published it already, so it is published. Oh, previous quizzes. Oh, okay, I see. Okay, thank you, Nicholas, for the clarification. Yeah, so I guess it does need me to grade those first before you can look at it again. Okay, so I can go ahead and try to grade everything as quickly as I can, and so you can take a look at your submission. All right. Alright, so what we'll do today is we are moving on to the von Neumann architecture and memory. We are basically done with double precision floating point number representation. Yes, we didn't quite finish the last part, which is normalizing everything to a 53-bit mantissa, and then shift the bits around so that we have a sign bit at bit 63, and then we have the exponent being 11 bits from bit 52 to bit 62. We didn't quite do all of that, okay, but it's really not needed, okay, for the homework assignment. For the test, on the other hand, for the exam 2, you do have to understand how to do all of that and be able to, you can do all of this and verify your own answer to make sure that your method of doing the conversion is correct. I illustrated the technique of doing that when we first started to talk about floating point number representation, so you can kind of replicate that process, just so that you know how to do everything by hand and not just using a program. All right, so I'm just checking, making sure there are no additional questions. All right, so the new topic is von Neumann architecture and memory. And I'm not sure about you guys, but when I hear about a von Neumann architecture, the first thing I want to know is, why is it named von Neumann architecture? I mean, who is this guy with a last name of von Neumann, and how is a von Neumann architecture different from all the architectures before von Neumann architecture? So those would be kind of natural questions that I will be asking obviously different people have different approaches of doing things, and some people may not, want to know all of this stuff here. So we just look up, von Neumann, and we find, the first link is not about the architecture. It is about the person who came up with the architecture, which is also a very interesting read. John von Neumann is basically a genius. Okay, so he's a genius in basically all of these fields. He's a mathematician, physicist, computer scientist, engineer, and a polymath expert. I don't even know what that is, right? So there's a rumor that his time at, I think it's Princeton University, coincides with Einstein's time, with Albert Einstein's time at Princeton University, and they their offices are in the same hallway. Einstein, being a kind of introvert, prefers quiet and peaceful type of environment, and then von Neumann, on the other hand, enjoys polka music of all things. Okay, he enjoys polka music, so you can probably kind of guess how those two may not get along very well. So anyway, von Neumann architecture is interesting because before that, let me show you computers before the von Neumann architecture. Okay, so you can look up computer wire wrapped before von Neumann. Okay, there we go. Okay, I know I had a typo, but that's okay. Alright, so one of the pictures you can see from let's see, I'm just trying to look for a picture. This one, oh, this is a good one right there. Okay, so this is a good picture of wire wrapping, and this is only for a 16-bit adder, and is wire wrapped. You can kind of look at all the connections between these. This is called wire wrapping, where there are special kind of wires. I think those are all 30 gauge wires, which is really thin. And then there's a special tool. All of these pins are pretty tall, and there's a wire wrap tool that has the wires exposed portion basically wrapped around the post a few times. There's a standard of how many times it's supposed to wrap around, and it is a point-to-point type of connection. So before von Neumann, all computers are interconnected. All the components inside, they're connected similar to this. Only worse, right? Because in this case, we are already looking at integrated circuits, which means they're relatively small already, so the footprint is not quite as bad as components back in von Neumann's time. So in von Neumann's time, integrated circuit probably did not even exist. So you're looking at a huge circuit board with basically plug, we call those things banana plugs now, but basically they're all directly wiring from one point to another. So if you want to change the behavior of quote unquote a program in one of those really old computers, it involves actually physically rewiring the computer itself. So I can probably imagine changing a program on those really old computers is a chore, okay, which it was. Okay, and the contribution of John von Neumann is he came up with a brilliant idea that we are taking for granted these days. So his brilliant idea is, well, instead of hardwiring the behavior of the interconnection of components inside a computer, why don't we utilize the computer's memory to also specify instructions and what the program or what the computer is supposed to do? Oh, okay, thank you, Chris. So he died before integrated circuits became a thing. So that means those computers were gigantic. Okay, it's physically a chore just to rewire computers so that they can behave differently. So getting back to von Neumann's contribution, so his idea was actually very simple in a way. Because even computers back in those times, they had memory already, because you need memory in order to store the data that is being processed. Okay, all the data points, all the computation and the result, all of that still needs to be stored in RAM. Okay, read-only access memory, or what is equivalent to read-only access memory at the time. So von Neumann's idea was to use the memory to, in addition to using the memory to store data, why don't we also use that memory to store instructions? Okay, so by the time, so we take it for granted, right? Because we started off with computers, okay, where programs need to be stored, loaded into memory before they can execute. So we kind of take it for granted. It's like, okay, so what is so special about this, right? But before his time, things were completely hardwired. So there's no such thing as let's download a new program. There's no such thing. You can download, you can get a paper schematic of the new connection of a computer, and then you have to do it yourself if you want to get a quote unquote new app on your phone. Obviously in that case, those wiring will be super small. Okay, but the idea is still the same. Okay, it's the contribution of John von Neumann is tremendous when it comes to making computers more flexible, because now we can actually just change the memory content in order to change the behavior of a computer. So there's that. Just a little bit of background information for those of you who are curious, because hey, why is it called von Neumann architecture? So in addition to von Neumann architecture, these days we also have what is called the Harvard architecture, same as the university, the name of the university. Harvard architecture is a little bit different. Oh, okay. So Chris also added that John von Neumann invented merge sort. Cool. To answer Omir's question, if you go to the Wikipedia page and just go to the computer science section, there's probably a good summary of his contribution. And I wouldn't be surprised if there are biographies about him, about John von Neumann and his contributions to computing. The thing is, he doesn't really just contribute to computer science. He also contributed to nuclear physics. The reason why he passed away so early was partially, people think that partially because he got cancer when he was helping to develop the hydrogen bomb. So all kinds of interesting stuff about him. If you ask any person, like a mathematician or physicist, during his time, what they thought of von Neumann, they all would say that he's a genius. In other words, he's not just a genius in one field. He's a genius in every single field that he touches, which is which is amazing. Anyway, so as far as we are concerned, okay, what we'll do in this particular section, it's kind of long, right? This is kind of a long section because this is how we kind of segue into the processor itself. But before we can get there, we're going to start with this particular slide. And I hope you guys had some time to kind of read this ahead of me, because it can be a little bit difficult to read through, even though if you kind of read very carefully and then possibly use Logisim along the side to actually create the circuit, it's not too bad. Okay, so the first device that we are going to talk about is called the SR latch. Okay, so we'll talk about why it's called the SR latch. Why does it have a funny name? Is SR the initial of someone? No, it is not. Okay, SR has to do with the functionality of a latch like this. So this is the most basic memory device, and it is only consisted of 2 NAND gates. Yep, 2 NAND gates. Okay, so this is how I specify a circuit here. So instead of using a graphical representation, I'm using a text or slightly object-oriented text representation. So NAND 2 is quote unquote a class, input pin is sort of a class, output pin is sort of a class, and then circuit is an existing object, representing the circuit. And when we talk about a node in an electrical circuit, a node is basically just an abstraction of a conductor. In other words, it is connecting, so a node is a single logical conductor that connects multiple pins together. And over here we see that it is connecting the pin of S, which is an input pin, to one of the inputs of N1, and N1 is a NAND 2 gate. So I'm just going to use Logisim to show you guys what the circuit looks like, and then we'll go ahead and analyze what the circuit is going to do. How does it work? What does it do, and so on. So let me just do something really lazy. Oh, okay, I'm supposed to grab Java. Oh, okay, I have lost the last history entry using Java, so now I have to specify the full command to use jar Java.
Wait, Johnny.
Hmm?
Can you do me a favor? Can you get me a piece of ice?
Okay, you might want to mute the mic. Alright, so right, so specify the path to Logisim 310 .jar. There we go. Alright, so we got Logisim started, and we'll go ahead and draw the circuit. Okay, so the circuit has two input pins. Okay, so here's one input pin, and here's another input pin, and it's got two output pins. Okay, so it's got two output pins. Control D is duplicate, so that makes it very easy to make another copy of something. Alrighty, so I think Jackie, you might want to mute your mic. Thank you. Alright, so now we need two NAND gates. So we go to gates, pick out NAND, okay. And we only need a small one with only two inputs. So we'll go ahead and customize this so that it looks nicer. There we go. And then we have a duplicate. Alright, so here's one NAND gate, and here's the other NAND gate. I'm just looking at the design because I wanted to look semi-nice. Okay, so we'll go ahead and move this down a little bit. There we go. That should do it. Alright. So now we hook up the pins, right? So this pin goes here, and this pin goes here, and then the output pin would go to the output of the NAND gates. So it's pretty straightforward here. So now the question is, what are we going to do with the other two input pins of the NAND gates? So this is where things get a little bit interesting, because the way we do this, okay, Control Z. The way we do this is we take the output of one NAND gate, and then we put it into the other input of the other NAND gate, and we do the same thing. This is symmetric. Okay, so the design is very, very symmetric here. So this is called an SR latch. Okay, and let's go ahead and put some labels onto the pins. Okay, because this makes the discussion a little bit easier. So we'll go ahead and put some names. Okay, so we'll call this one S. We'll call this one R, and this is the non-negated output pin called Q, and this is the negated output pin, and we'll just call it NQ, okay, for not Q. Okay, so there we go. So we have a SR latch in this diagram. But instead of just looking at the diagram, and then use Logisim to figure out what it does, we're going to analyze, okay, to find out what it does. Andrew is asking, isn't there some sort of unstable behavior that happens when the latch is badly set up in real life? That's a very good question, and Luke already kind of answered the question. Yes, it can cause oscillation when both pins change from 0 to 1. Then the output would basically go into a cycle of switching between 0 and 1, and the period, the half period I should say, is going to be the latency of a NAND gate. In other words, how much time does it take for the input of the NAND gate to change to the time that the output also changes accordingly. That will become the half period of the oscillation. So we'll get to that. Okay, we'll get to that. Okay, this is going to be interesting. So the next thing I'm going to do is not to use LogicSim. So I'm using LogicSim at this point only to show you what the circuit looks like. And then what we'll do is we're going to use the tablet in order to analyze the circuit. So we'll do the analysis of the circuit manually. Okay, so I'm just replicating the design here. So we have S, we have R, and then we have the output here going to Q, and then we have the output of this guy going to NQ for not Q, and then input pins, each one goes to one of the pins of the NAND gates, and then the output of one NAND gate goes to the input of the other NAND gate, and this behavior is symmetric like that. Alright, so we got the circuit already drawn, right? So now we want to find out, okay, what does it do, right? So we'll create several truth tables. Okay, we'll analyze a few different scenarios. So we have S, R as the input. So S and R, each one is an independent variable when we want to look at this from the truth table perspective, because how we want to specify, when we specify the state of S, it is independent to the specification of the pin R, so they're completely independent. But we only want to look at one specific case for now. Okay, we want to only look at the situation when the S pin is 0 and then the R pin is also a 0. So we want to figure out, is it sufficient to tell us what Q and NQ should be in this case? So the answer is yes. Okay, it's actually fairly easy because it has to do with these are NAND gates, right? So as a NAND gate, negated AND gate, it means if at least one input of the NAND gate is a 0, the output is going to be a 1. Does that make sense? Because 0 and whatever is going to be a 0. But since the output of a NAND gate is the negated output of an AND, so that means whatever a 0 would become a 1. So in this case, Q and NQ would both be 1s. So do we have any questions about the analysis of the case when the S pin and the R pin are both 0s to begin with? And Aaron is typing something. I'm gonna wait for his question to be done. Alright, so okay, so it's a Codeblocks issue. Oh, okay. Yeah, if you rebuild the project, that should get rid of all the old object files, and then it would just recreate everything from scratch, unless the timestamp is messed up. Okay. Alright, so getting back to the SR latch analysis. So let's go ahead and look at the next state. Okay, so this is following this particular state. So we look at this as a state, and then we go like, okay, we'll transition to this state here. So once again, we're only looking at one specific scenario, and this time we'll basically say, let's go ahead and change the R pin from a 0 to a 1 and see what is going to happen. Okay. So let's analyze this one. Okay, and the way we will do this is I'm gonna use something a little bit fancy. I'm gonna introduce a second layer, so this way we can go back and erase the entire layer, because certain things we don't want to preserve. Okay, so in the first one, okay, we have 0, 0 here, and then we have 1 and 1 here. Okay, so that's the that's coming from the first state. So now we want to change it to the second state, where r is changed from a 0 to a 1. So this is a technique of analyzing how a circuit like this is going to respond. Is we are trying to follow the propagation of changes. Okay, so the origin of the change is this. Okay, we are erasing this 0 so that it becomes a 1. Okay, so Alexander, let's let's wait a little bit before we get to that part. Okay, but for now we are changing the R pin from a 0 to a 1. Okay, and we want to follow that change and see how that change is going to propagate and cause further changes down the line. So when this pin changes, when R changes from a 0 to a 1, then we want to see whether some changes will happen to this NAND gate over here. And sure enough, something's going to happen, because this wire has a 1 from S and R both being zeros, and now that we change R to become a 1, the input of this NAND gate becomes 1 and 1, which means the output is going to be a 0. Okay, so that's basically after one propagation. So this 0 in return is going to follow this path to the input of this NAND gate here. So our question now is that going to change the behavior of the top NAND gate? And the answer is no. Okay, the propagation stops right here, because the top NAND gate already had one of the input being the S pin being a 0, and we only need at least 1 0 for the output of the NAND gate to become a 1. So the fact that we are changing this particular wire from a 1 to a 0 doesn't really change the output of the top NAND gate. So the output of this particular state change is Q remains to be a 1, and then NQ becomes a 0. So are we good so far with this analysis? All right. Okay, we got some. All right, so thank you for the confirmation. So now we go one step further. Okay, we now ask, what about this? Okay, what about S and R both become 1s? Okay, so we have 1, 1 here. So now we want to make another transition to this new state. And the only transition is S, which was originally a 0, is now becoming a 1. And we want to analyze what it looks like. My NQ0 looks like a Q. Yes, it does, because I was because I mistyped it as a Q. Thank you. Alright, so getting back to here. So now we are changing this pin from a 0 to a 1. And now we want to follow the changes again, right? We want to follow the propagation of the change. So we now say, okay, this one is one of the inputs into this particular NAND gate here. Is it going to cause any changes to the output of this NAND gate? So now you have to kind of think about it, because this is already a 0. This wire already has a 0 in it. So as I said, you only need at least one input of a NAND gate to be a 0 for the output to be a 1. So there's actually no change to the output of the top NAND gate. And as a result, the propagation of change stops right here, because it doesn't really cause any changes. So that means the Q pin will remain as a 1, the NQ pin will remain as a 0. So now we have a 1 and a 0 here. Okay, so are we good so far? Alright, so let me see if I can just copy and paste this into a new page so that we can compare and contrast with the next example. So we'll go ahead and specify the selection tool. Okay, And then we'll copy first and paste. So we'll paste on this side. Oh, doesn't let me do that. Okay, let me do it one more time. Copy. Oh, okay, tap on any page with marker to paste. So paste, there we go. So now we want to move this to the right place. And it's only pasting one layer at a time. It doesn't quite select all of the different layers. That is not what I wanted to do. I'm just reading the text channel right now. Okay. Alright. So let me see if there's a way to select multiple layers. So the selection tool only works on one layer at a time. That is not that is not convenient at all. Alrighty. Okay, I know what to do. We'll switch back to layer 1 and go back to the selection tool, and so we'll leave this one alone, and then we just have a different starting point. So this is the starting point. No, it's selecting the wrong layer again. Alrighty. Okay, so even though I have layer 1, selected here, the selection tool is always going to use the top layer. So let me see if I can switch the layer order and try that one more time. If this doesn't work, we'll just go ahead and replicate things, manually. Okay. Select the whole thing. Nope, that does not work. Alright. Time to send in the bug report. That's okay. So we'll go ahead and do it the hard way. So doing it the hard way, this is one path, and then we'll basically just do this. Oh, okay, wrong tool. We'll basically replicate the whole circuit. Okay, so this time I'm just gonna do it really quick. Like so. Okay, there we go. So we got S, R, Q, and Q. And we're going to start with the same start state, which is S and R, both being zeros. And as a result, both outputs are going to be ones, okay, just like last time. So this one is identical to the last one. But then the next one is going to be a little bit different. So this time we are going to change the S pin from a 0 to a 1, and then we are going to preserve the R pin from, so that it remains as a 0. So now we have a different transition. And because of the symmetry of the circuit, you can probably quickly conclude and go like, oh, okay, so we're just going to change the states of Q and NQ so they become opposites of each other, because the circuit itself is symmetric. Okay, the top half and the bottom half is symmetric. So we're basically just looking at a circuit in a mirror image, so to speak. So now we go like, okay, so we will change Q and NQ. So Q becomes a 0, NQ becomes a 1 this time. So the tricky part is, what if we also choose to turn R into from a 0 to a 1? That becomes the interesting question. Okay. All right. So to do this part, we're gonna have to label the wires, based on the second state, which is this one here. So we have a 1 over here, we have a 0 over here, and then the output of Q is going to be a 0, and then the output of NQ is going to be a 1. Okay, so now we make this transition so that we have both inputs being 1s. S and R are now both 1s, but the only transition, the only change is R changing from a 0 to a 1. So now we try to follow the changes. So R goes from 0 to a 1, and now we try to follow the changes, right? But you can see that for the bottom NAND gate, it's already getting one of the pins getting a 0. So even though we are changing the input pin R from a 0 to a 1, it still has at least one input being a 0. So that means it will continue to output a 1, and the propagation of changes will stop right here. So that means we are not going to see any changes as far as Q and NQ are concerned. So Q is going to be a 0, NQ will continue to be a 1. So when you look at the two paths, okay, this path and this path over here, this is something that we haven't seen before, right? Because if you look at the third state of each path, you can see how the inputs are the same, right? S and R are both 1s, but the output states are different. Okay, one has Q being a 1 and NQ being a 0. And once again, I'm using the wrong symbol, and it won't let me erase it because I'm just gonna do the hard way. Okay, so this is a 0. But the other one is opposite. Okay, we have SR, S and R both being 1s, and then Q is a 0 this time, and NQ is a 1 this time. So this is why it is called a latch, because it's storing the state, okay, so to speak. It is storing the state, when we get to both R's being 1s. It is basically preserving the previous state at this point. Oh, Nathan asked, is there a way to merge the layers? As far as I could see, there's no way to merge the layers. So we cannot flatten the layers. And Alexander is correct. It depends on which one gets in, which one is changed first. Okay, but I want to show you guys why this is a memory device, even though it doesn't look like it. It is a memory device. So do we consider NQ as not Q because of the circuit? It is because both inputs being 0s is a unusual input state. Okay, typically we only want one of the inputs to be a 0, but starting with both inputs being 0s is unusual. But in this particular example, we want to have the same starting point, and that's why I want both S and R to start with 0s along both paths of the analysis. And you can definitely tell that when both S and R are 0s, Q and NQ, they both have 1s. So NQ is not exactly not Q in this case. Okay, so Nathan has this interesting question about why RAM needs to be powered to maintain its state. So an SR latch still needs power, very, very little power to maintain the state, because the transistors still need to be powered. Okay, so it doesn't really have quote unquote any current draw, because the transistors are basically a capacitive load, which means power is only used when we change the state of a transistor, when we change the gate pin of a transistor. That's when power is actually used. But what we see now in computers is called dynamic RAM and not static RAM. So static RAM, as the name implies, means you can maintain the content of RAM by using a very, very small amount of current, and it can maintain the state. That's static RAM. And then dynamic RAM, which is DRAM, is the one that needs a refresh, because it is basically using the capacitive property of transistors to maintain its memory. So that's why you need a refresh once in a while, to basically say, hey, this capacitor is about to lose its capacitance. Let's refresh it, so that it maintains the state. And that's why you have SDRAM. Okay, when you buy a computer or when you buy extra memory for your computer, the memory that you purchase is called SDRAM, which sounds really weird because most people think SDRAM stands for static dynamic RAM, which is not the case. The first S stands for synchronous. Okay, it stands for synchronous dynamic RAM. Um, and the and then you have DDR2 and all of the other technology involved. DDR2 is a whole different kind of game. It has to do with when we update something or when we retrieve content from a location in memory. Do we need to specify the address over and over again, even though the addresses really are sequential? Okay, we're just reading sequential bytes or sequential words out of the RAM. So DDR is a technology that basically says, nope, you don't have to specify subsequent addresses. You specify the starting point, and then the RAM and the processor has an agreement and go like, okay, we're gonna do 64 reads, or we'll do whatever n is. Okay, we'll do n reads, and then each read will read the following word, so that we don't have to specify the address over and over and over again. So that's the DDR technology. So I'm digressing, but it's interesting how those things work. All right. So I'm hoping you guys are all seeing, at least graphically, how the SR latch is a very rudimentary, a very simple memory device, because once we set the output pin Q to a 1, then we can go to a maintenance state where Q is maintained as 1. Once we reset, okay, so R being a 0 is resetting. So once we reset Q to a 0, then we can go to a maintenance state where both S and R are both 1s, but we maintain the state that Q is a 0. So this is why the SR latch is one of the most rudimentary memory devices. It's easy to understand in a way, because when we look at this in this particular way of analyzing it, it's relatively easy to analyze. But it is not easy to use, because instead of saying, hey, here's a data pin, it's either a 0 or 1, and just go ahead and remember the state of the data pin, it's not quite like that, right? Because we have one specific pin to say set the memory pin to a 1, and then the other one to say reset the memory pin to a 0. So it's not quite that easy to utilize, but nonetheless, it is a kind of interesting circuit. Alright, so I'm open to questions at this point, and Jonathan is typing. So Q is usually considered the quote-unquote output, the non-negated output of an SR latch, and then NQ is just, it has to be here, okay? So even if you don't connect the output of the bottom the NAND gate to its own output pin, it's still needed. I mean, you still need this output pin to go all the way back to one of the inputs of the top NAND gate. So, in this case, we're just gonna okay, why don't we use a pin to also capture the output of this NAND gate, okay? Because it does come in handy in some cases. It's just that not in all cases. Yeah, I think the SR latch is a very cool design. It is simple, it's elegant, and it gets the job done. Okay, so whoever invented the SR latch, is, I would say, is a genius. So why does the SR latch have more I/O pins in Logisim? Nope, I think it still has the same. And to answer Victor's question, I believe the SR latch is still being used. May not be in this exact form, but it is still being used in order to implement registers inside the processor. And then we got Marco asking a question. It has a preset clear and clock input in Logisim. That is correct. That's why we have a relatively long module, so that we can go from the simplest SR latch and then go all the way to the more complex SR latch. So the one that Nathan has quoted, has an enable pin, which basically is it's acting like a gate. So if when enable is a 0, then the SR latch does not respond to the S and R input pins. And then the 0 is basically a universal reset. Basically, when your computer first start up, you don't want the bits of your memory to be random, or at least your registers. Memory can be all random, but you don't want your registers to be all random. So at the power up phase of a processor, there's a special pin called the reset pin. The reset pin is held, I'll just say held asserted, okay? Because it's inverted logic, so that can add to confusion, but it's asserted. So basically that tells every single component inside the processor to go like, okay, reset to your default state, okay? And most registers reset to zeros. It doesn't have to be, but most registers reset to 0, and that gives your processor a known startup state, which then can be used to fetch additional instructions and whatnot. Yes, we're gonna talk about flip-flops. The one that we are talking about here is not a flip-flop. This is just an SR latch. Flip-flops are larger devices that we use SR latches to make. Cool. We are not going to talk about parity bits. Parity bits, for the most part, is not very useful because a parity bit is usually used to detect errors, but it can only detect errors where the zeros and ones, or the number of ones, is odd versus even. So if you have two errors, they can cancel out each other so that the parity bit cannot detect the problem. So we are not going to talk about parity bits. All right. So in Logisim, it's called the SR flip-flop because it is not exactly a very simple SR latch. This, what I have here, or this, what I have in Logisim, that is a simple SR latch. This is basically as simple as it gets. So with this one, we can we can now experiment, just kind of replicate the experiment that we did earlier. So we can flip R from a 0 back to a 1, and then we flip S also from a 0 to a 1, and you can see how it is quote unquote remembering the state of a 1, because we consider Q as the quote unquote output, right? So now the SR latch has an output of 1. Now if we follow the other path, okay, resetting both pins to be zeros to begin with, and this time we are changing the S pin from a 0 to a 1, and then we change the R pin from a 0 to a 1, and you can see how this time it is remembering the output of the SR latch to be a 0. So in Logisim, this is you have to construct your own SR latch if that is what you need, because the simplest device that that Logisim offers is already a flip-flop, which is not this. All right. So do we have any questions about the SR latch or how we analyzed the behavior of the SR latch? No questions? Okay. Oh, here comes one. Okay, so in order to store memory bit, you need 2 inputs. Yeah, so it's not exactly a very easy to use memory device, but nonetheless, it has the property of it can maintain the state. That's why we have the module. That's why I wrote the module that we are reading here. we if you look at the thumbnail, we are at the very beginning part of this module. Okay, so there's that, and then Omer is typing. Oh, wait, maybe not. All right, so we're gonna scroll down to the next device. So the text, all this text here is really just, using text to explain the same thing that I just talked about. So there's no new information there. So now we talk about the D flip-flop. Okay, so D flip-flop is a little bit more advanced. So when we look at the components, we can see it has a NOT gate, it has 2 NAND gates, it has a SR latch, it has 2 input pins, and it also has 2 output pins. And this part here, basically shows how the pins are connected. And by the way, using text to describe the connection of components inside the processor is the job of a hardware, HDL, hardware description language. Okay, hardware description language. There are 2 main HDLs, okay, used in industry. One is called VHDL, and the other one is called Verilog. For those of you who are planning to transfer to Berkeley into their computer science and engineering degree, I believe the final year project is to extend a basic design of a processor using, if I remember correctly, I could be wrong, using Verilog, and the assignment or the project is to add additional features to that processor. So that's going to be specified in a text form, maybe not like exactly like this, okay, but something similar to this. So the good thing about being able to specify how components interconnect in text form is now you can specify loops, conditional statements, subroutines, and so on, so that you can create large and complex design using algorithms instead of having to do everything by hand. So there's that. Okay, so now we're going to take a look at a D flip-flop, and then we'll go ahead and construct the circuit. So I hope you guys have your own browser open, because this way, I can move the browser aside so that we can focus on Logisim while you can, continue to read the D flip-flop design as I talk about it. So I'm going to do that right now, moving the browser to the side. And what I'll do here is to turn this into its own circuit. So we'll go ahead and go to the design appearance mode like this, and then we'll just label a few pins. Okay, it's not really needed because the inputs are fairly self-explanatory, but we'll go ahead and label these things. So we have the S pin, the R pin, the Q, and the symbol for Q, the slash symbol, a lot of times also means negation when we look at the nomenclature of pins in a on a circuit. So that's why I use slash Q in this case, to mean it is the negation of Q. So we probably have enough space inside the chip to put everything. Okay, that's exactly the case. Very nice. Okay, there we go. Alright, so now we have just created our own component. It doesn't make sense to call this main because we're going to use it as a component. So we'll go ahead and change the name of this particular circuit to SR latch. There we go. So now we can utilize the SR latch in our next circuit. And where I put the browser is covering this chord, so now I can read this chord here. Okay, so there's nothing new on Discord. Alright, so we'll go ahead and go to project, add circuit, and this time we have a D flip-flop. I'll just use DFF as the name of the D flip-flop. So getting back to the notes, okay, I hope you guys have this open on the side. We'll go ahead and pull all the components first, and then we'll basically do all the interconnection between the components. So we need one SR latch. Okay, so it's kind of like cooking, right? We're just getting all the ingredients first, and then we have under gates we need one NOT gate. Okay, so we pull one NOT gate, and then we need 2 NAND gates. Okay, so we need 2 NAND gates, and we want to change the size to narrow and the number of input pins to be 2. And duplicated because we need 2 of those. What else do we need? We need 2 input pins, 2 output pins. Okay, so we need 2 input pins. Here's 1, duplicated. We got 1 more. And then we have 2 output pins. Here's 1, duplicated. Now we have 2 output pins. There we go. And we got 1 question coming from Zoe. Oh, I put and not NAND. Oh, you're right. Okay. Duh. Okay. The circuit did call for NAND, and I accidentally put a AND gate instead. Thank you. So we'll go ahead and change this back to where it is, what it's supposed to be. There we go. Alright. So the nice thing about LogicSim is it also allows you to label things. Okay, so we'll label the input pins. One is D and one is EN. So D is the shorthand of data, and then EN is the shorthand of enable. The 2 NAND gates, one is called N1, so we'll label this one as N1, and then we'll label the other one as N2. I'm just checking the text. There we go. Thank you. Well, I did the correction. And then the output is once again just Q and NQ. So once again, Q is the output of the circuit. NQ is for the most part, since it's free, we have it available, why not, right? So we have NQ, which is, in this particular case, it is always the opposite of Q. And then the NOT gate has a very simple name of N, like so. And there we have it. Okay, so now we have all the components. Now we need to specify how they all interconnect. So the D pin goes to the first input of N1. Okay, so here's N1, and we'll start with a straight connection from D to the first input of N1. It also goes to the input of the NOT gate. Okay, so here's the NOT gate, and we're gonna put it maybe here. And D also goes to the input of the NOT gate. We'll move the EN pin down a little bit so that we have room to draw other connections. So EN goes to the second pin of N1. Okay, so this may not be the most elegant way of drawing the circuit, but you know, it's gonna work. It also goes to the first input of N2. So here's N2, so we want this to also go to the first input of N2. And then we have the output of N going to the second input of N2. Alrighty, so we need to pull this out a little bit so we have room for making this right angle. Yeah, this is not the best looking type of circuit, but you know, as long as it's functional, it's fine. And then we have N1's output going to SRS. So so this component can have its own name, you know, which is SR, which is really unreadable because it's 90 degree and it's inside the circuit, so it's not going to be very helpful. Oh, here's another label, so maybe this will help. The other one is shared, and we don't want to specify the shared label. So SR is this particular component, and the S pin of SR connects to the output of N1. So we align everything so this at least one part of this looks nice, like that. And then N2's output go to SR.R. So we go here, and then we go here. And then the output Q goes to the output pin Q. Okay, so that part is pretty easy. Yeah, we got the circuit mostly done already. So this one goes here, and then /Q, which is the abbreviation of NQ, you know, the negation of Q, goes to NQ over here. Okay, so now we're done with the circuit. The first thing we do is, hey, how come there are red pins? Red pins are bad, right? Because it says error. Well, that has to do with, for this particular SR latch, the initial state is to have both inputs being 1s. And from the previous discussion, you probably remember this is how we maintain this current state of an SR latch. But there's no quote-unquote current state to maintain because we never specified what the initial state of this SR latch should be, and that is the reason why the output is 2 red wires, because we never really specified what the initial output of the NAND gates inside the SR latch should be, and as a result, there's no way to actually determine, what is the current state of the SR latch. So that is the reason why we got the red wire. Okay, so we can fix that once we specify the behavior of the D flip-flop. All right, so let me first describe the overall behavior of a D flip-flop. Yes, you can use an AND gate, and then no. N2 has to be a NAND gate, cannot be a AND gate. Not sure what Victor is referring to, because this is N2, and the behavior of a NAND gate and an AND gate is very different. So with this one, I think it has to be a NAND gate. Now you can basically get rid of this NOT gate and change the second input so that by itself is negated. We can do it that way, but this is more spelled out that we are negating data before it becomes an input into N2. Okay, so the first thing I want to do is to just kind of describe the overall behavior of a D flip-flop. So a D flip-flop allows you to separate what bit you want to remember and when you want to remember it. Okay, so EN being a 0 basically means no matter how I change the D pin, nothing is going to happen to the SR latch. Okay, so that's the first thing that we want to analyze and go like, but how? How is it possible that when the EN pin is a 0, it doesn't matter how we change the D pin, the SR latch does not get affected? Well, that turns out to be pretty easy, because you can see how the EN pin is an input pin not negated into both N1 and also N2. So that means as long as EN is a 0, N1 and N2 are both guaranteed to output 1s, regardless of the state of the D pin. So that means if the EN pin is a 0, we are basically essentially asking the SR latch to say, hey, maintain your current state, don't change a single thing. So that is why, when the EN pin is a 0, you can go ahead and change the data pin and nothing happens to the output of the circuit. You can see, that doesn't really change anything, because N1 and N2 are both going to output 1s because EN is non-negated connected to both of these pins. So now the next question is, so that means when EN is a 1, then we actually can change the SR latch, right? I mean, that's just kind of logical that we, that becomes the next thing that we want to understand. So now we turn, but before we turn EN from a 0 to a 1, let's analyze what's going to happen. Okay, so when we change EN from a 0 to a 1, that means N1 now has one of its input being a 1, and N2 also has one of its input being a 1. So that means at that point, when EN is a 1, the output state of N1 and N2 will solely depend on the other pin. Because remember, this is a NAND gate, which means, if an input pin is a 1, that input pin is no longer useful to determine the state, the output of the NAND gate. It would depend on the other, input in that case. But the other pin for N2 is the negated version of D, and then for N1 it is the non-negative version of D. So that means when EN becomes a 1, the output of N1 and N2 are guaranteed to be opposites of each other. Okay? And the other thing we also know is when D is a 0, n1 is guaranteed to be a 1, but if en becomes a 1, then n2 has got to be it's going to output a 0, which will then reset the SR latch, which means the output pin Q is going to be a 0. That is how it works. Okay, so let me just illustrate it in Logisim. Logisim doesn't really show the the propagation of changes. It just does it right away for you. Okay, so it's a good way to verify the behavior of a component, but it is not a very good way to gain an understanding of how a circuit works. Okay, so we'll go ahead and do this. Okay, so we'll turn enable from a 0 to a 1, and you can see right away the SR latch is no longer outputting 2 red wires, because right away we basically specify that we want to reset the SR latch, and as a result the output Q now becomes a 0. It is reset to a 0. If we as long as En is a 1, whenever you change the D pin, the Q pin will mirror. So if we change the D pin from a 0 to a 1, we can see how Q is basically just mirroring the D pin. So this effect stays as long as En is a 1. But the moment we turn En from a 1 back to a 0, then the D pin no longer changes the SR latch. So this is called a D flip-flop. Well, I can do better than that, Nathan. Well, more or less. It may be better, may not be better, but we can read what I have typed here. Yes, I know it's going to be a headache because oh, maybe not. So the so if you want to make a truth table, okay, we are running out of time today, but I can finish this portion. So let's switch back to the tablet so we can finish this part. Okay. Oh, it has gone to sleep. Alright, so let's open a new page and basically use this to analyze the circuit. Alright, so you probably don't need a full truth table for a D flip-flop, because once you get to the input of the SR latch, I assume that we already understand the behavior of an SR latch. So when we get to the output of the 2 NAND gates, then we should be good, right? So the truth table is going to be, here's D and this is En. So these two are the independent variables, and here is Q and here is NQ. So when En is a 1, the analysis is pretty easy. Okay, if D is a 0, Q is going to be a 0. If D is a 1, Q is going to be a 1, and then NQ is really just the opposite of those two. So now the question is, what if En is a 0? So this is a little bit difficult to specify in the truth table, because it does not matter anymore what D is. D can be a 0, D can be a 1, but Q is maintained. Okay, so it is basically just maintained. And same with here. So whatever it was from before, it will continue to be like that. So that is a little bit hard to describe using a truth table. The truth table that I had in my notes is for the SR latch. So this is a truth table for the SR latch. So I use NC to represent no change. Oh, you guys cannot see where I'm referring to in the module. So this is where I'm referring to in the module. This is inside the SR latch discussion. But in the truth table that we are constructing right now, instead of using maintained, I'm going to use the same terminology, NC, 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 and NC here, and then NC is the same as no change. So does that answer the question of the truth table of a D flip-flop? Alrighty. Okay, so we are done for tonight's lecture. So we are only about halfway through the module. Let me put the module back into view. There we go. Alright, so we're only about halfway through because the next one is called a okay, there we go. The next one is called an edge sensitive D flip-flop. And this is the one that takes even more analysis. So if you look into the analysis of an edge sensitive D flip-flop, there are quite a few different states because it's a very interesting design. The edge sensitive D flip-flop is more complex compared to a normal D flip-flop because it is sensitive to an edge. Okay, it's sensitive to a transition. So when the particular pin goes up from 0 to 1, that is the moment that the output pin will change to the state of the data pin. And as a result, it's a more the explanation of an edge sensitive D flip-flop is more difficult. And then we have a clocked and gated D flip-flop, and this one is also interesting because it's kind of the combination of the original D flip-flop and a edge sensitive D flip-flop. And of course, there will be questions of, but why do we make all of these more and more complicated things? So in the next lecture, I will try to explain some of that stuff. And then we have the last one, which is a resettable edge sensitive and levels and edge sensitive D flip-flop. So this one is even more complex. You can see how it is using 3 SR latches on top of 2 AND gates, 1 OR gate, and another AND gate over here to make this particular design. And then we have a multi-bit version because each of these components here is actually something like this. So when we have 8 of those things connected in a particular way, we call that a register. Okay, so this particular module takes you all the way from a very simple design using only 2 NAND gates, and we know that a NAND 2 gate can be implemented using only 4 transistors. So using only 8 transistors, we can make the smallest memory device called an SR latch, and it just takes you all the way to section 8, which is a multi-bit register, and this is one of the most crucial components inside a processor. Okay, and after this we'll get into the pathways between the registers in the design of the actual TTP, which is tax toy processor. So that's kind of the layout of the topics at this point. So if we are on schedule, by week 8 or so, we'll start to program using the processor that is going to be constructed using all of these components. Nope, this is not a shift register. So with a shift register, the output of one basically D flip-flop goes into the input of the next D flip-flop. That will make it a shift register. So that for each clock, for each transition, the data will go from basically go from one to the next one. Yeah, that's what I thought too. This is really kind of cool because this particular module goes all the way back to something that we talked about on day 1, which is the NAND gate. And using NAND gate and some other really simple gates, like AND or NOT gates, we construct basically one of the most useful components inside a processor, so that the processor can say, hey, where am I supposed to be executing from? What is the next location that I should get an opcode? Because the processor needs to remember that, right? And a register is what we use inside the processor as little post-its. Okay, where am I supposed to read next? Okay, or what is the partial result of this calculation? What am I adding? Where am I supposed to put the result of the add? And so on and so forth. Okay, so all of those things involved the use of registers. That is correct, Chris. Registers are in CPU, they are not a part of RAM. RAM is very slow devices compared to registers. So registers can keep up with the ALUs or the FPUs. An ALU is the arithmetic and logic unit, that's the ALU, and then a FPU is the floating point unit, which is basically kind of like the ALU, but it applies to double precision floating point representation. But basically, those are really fast circuits. Remember how we use carry and borrow look ahead to try to make the adder as quick as fast as possible. So those calculations can happen, really, really fast. Okay, for every single clock of a 4 gigahertz processor, it can perform a complete add instruction. Okay, so now the question is, where am I supposed to put the result of addition, subtraction, comparison, and so on? Well, the answer is registers, okay? Because registers are very fast. They can keep up with the speed of the ALUs. Memory devices or memory chips, okay, that we normally know as DIMMs, DIMMs, for dual inline memory module, okay? Those things are outside of the processor chip, okay? So for one thing, they are further away, and that distance, would automatically add latency to how fast we can transfer content between the processor and RAM. But that's not the only reason why RAM is slow, because RAM is registers, are not very cost effective from the perspective of how many transistors we need to remember one bit. DRAM, on the other hand, is very frugal when it comes to the use of transistors and the use of silicon, but it comes at a cost of it needs to be refreshed, and because of the huge memory space, it also needs time to decode the address. It's like, okay, this DIMM is responsible for 4 gigs of RAM. Which location do you want to access? That takes time to decode. So by comparison, if you look at the scale of how quickly we can update a register and how quickly we can update a location in RAM, there's no comparison. Okay, anytime you need to go out of the processor chip to access memory, it incurs a huge cost in terms of time. You can think of registers as little post-its that you keep handy, on your desk inside a classroom. Okay, so it's very handy. Okay, you need to jot down some numbers. Okay, pretty easy, no problem. Okay, using that analogy, memory content in memory is almost like a notebook that someone keeps in the library. So you have to walk out of the classroom, walk all the way to the library, get to the right floor, get to the right shelf, then you can access that content. It is slow. Okay, by comparison, accessing RAM is very, very slow, and that's why we have cache. Okay, that's why most processors now have cache. So cache is kind of like it's transparent to software. In other words, you cannot specify whether to cache a memory location or not. Registers are not transparent. Okay, registers are not transparent in the sense that you can specify, hey, I want to use register A to remember this, and then I want to use register B to remember that, and so on. So it can be specified by software. Cache is transparent to software for the most part, and what it does is a localized copy of some content of a notebook in the library. So at the door of a classroom is a pile of paper. Okay, so if a page is recently accessed, it has a copy in that pile of paper. So if you're lucky and you're accessing a location that has been recently accessed by somebody else, then you can just use the quote-unquote cached copy without having to walk all the way to the library. And then there are different levels of cache too. So there's level 1, level 2, and level 3 cache that I know of on the chip, and they basically represent how far the cache mechanism is away from the registers. So level 1 is the closest, level 2 is further apart, and then level 3 is the furthest before we have to go out to memory. Um. Oh yeah, hard drive are much slower. we're talking about orders of magnitude here, because with a hard drive you need to wait for the disk head to move, and that is measured in milliseconds. Inside the processor, with a 4 gigahertz clock, you're basically completing an addition and be able to store something into a register, um, basically 4 times per nanosecond. So that is really, really fast. Is it nanosecond? 1 gigahertz is. Let me see. Let me think. 1 megahertz. The reciprocal is 1 microsecond. So 1 gigahertz, the reciprocal is 1 nanosecond. So we can update, like 4 times per nanosecond when it comes to registers. Cache is not quite as fast, but it is still much faster than having to access memory. Because when you access memory, you're talking about. Yep, thank you. Um, Thank you, Chris, for the units. So when you think about accessing memory, when you go buy memory, they will tell you the clock rate of those memory modules, and they are usually still in hundreds of megahertz. So it's off by at least one order of magnitude compared to the speed of registers. Yeah, well, it depends on which part of the CPU. The question is CPUs are in nanoseconds. So it depends on which part of the CPU you're talking about. If you're talking about how fast an ALU can complete an addition, yes, that is actually in the fraction of a nanosecond. Because with a 4 gigahertz clock, you can basically, if we assume one clock per instruction, which actually is not even true anymore, we can actually have multiple additions per clock. So but even if we assume one clock per update of the ALU, we are still talking about a fraction of a nanosecond, if my math is right. Yep, this kind of time scale is crazy. I mean, if we are to talk to John von Neumann now and say, hey, we can finish one addition in a fraction of a nanosecond, he'll look at you and go like, are you really sure you got the unit right? Core memories are slow because core memories are based on magnetism. It takes time for electromagnets to change its polarity. In fact, it's really slow because you have to fight inductance for that to happen. And also the density is really low too, because you're talking about tiny little magnets with winding in the coils. We have come a long way from using core memory. Alrighty. So or we can use relays. We can use relays to implement NAND gates, because remember, a relay is kind of like a transistor, so you can find the equivalent of a P and N, quote unquote P and N type relay. So using relays, you can basically implement a NAND gate. So that would be awfully slow, but it will make some really interesting sound because it will click a lot. We do not have a lab that is due tonight. Okay, so we do have a lab, quote unquote lab, but it's more like a week-long assignment that is due next Tuesday. Yep, so that's the only one. Oh, okay, I might check that out. The hidden language of computer hardware and software. Cool. Ooh. Well, you guys are reading more than I do. Yep. Well, we're gonna build our own ALU too, because now that we know how to implement a carry look ahead and also a borrow look ahead adder / subtractor, that accounts for a lot of things that the ALU does. So on top of that, the ALU also has a right shift operation, because there's no other way to implement right shift unless you have it built into the hardware. But right shift, using basically shift registers is actually pretty easy to do. I'm pretty sure if I use Minecraft instead of Logisim, nobody will be. We won't be able to get past week 4. Not because it's a pain to build, but because we will get distracted. Playing Minecraft isn't the fun part. Programming Minecraft is the fun part. How do you make modules, to run in Minecraft? And that, for the most part, is because Minecraft is written in Java, so you can replace a Java bytecode module easily and change the behavior of the program. Yeah, breadboard computer isn't cheap, and it's not really a good use of time either. Other than, yes, I built it. No, I do not make Minecraft mods. The person that you should ask about Minecraft mods is in this class. If Caleb is still here listening, he is the guy to ask if you want to learn how to make Minecraft mods. Yep. Alrighty. So I'm gonna step away for a little bit, but I'll keep an eye on the text channel, because it looks like we got all the class material done. So I'm gonna stop screen sharing, and I'll step away for maybe 10-20 minutes, and then